Just now we have mentioned that we do not need to use two lines to represent permutation. We can write it into cycles for representation, but it may be still not enough. Let's think over here. Is there any other different representations? For example, 1, 2, 3 need to be changed to 2, 3, 1. It can be regarded as switching between 1 and 2. Then it could be 1, 2, 3 is changed to 2, 1, 3. Then operated with a switching between 3 and 1, which is 1, 2, 3, 3, 2, 1. Looking at these two different permutations, what are they? The first permutation is the switching between 1 and 2. 3 remain unchanged. Well, the second permutation is actually 2 remain unchanged. 1 exchange with 3. We can write it down with a multiplication of 2 cycles. Each cycle contains 2 elements, which is called swap. And this time the permutation 1, 2, 3 to 2, 3, 1 is turned into the product of 2 swaps, which is 1 is swapped with 2 multiplied by the swapping of 1 and 3. Therefore, corresponding to any cycle, it can be written as a product of several swaps. Over here, we can use it to prove, we managed to prove the cycle of 1, 2 until n-1 can be written as 1 change to 2, 1, 2, 3, continue to with the same way. Then if we want a longer permutation, we would like to prove 1, 2, 2, 2, 2, 3 until n. Can it be written as a swap of 1 and 2, swap of 1 and 3, continuously accumulated the multiplication until 1 is swapped with n? We will split it into 2 parts. First, 1, 2, 3, 1, 2, 2, 2, 3 continuously change until n-1. And last, we have a permutation. 1 is changed to 2n. If multiplied then together, what will be the result? We know the permutation can be written as a 1, 2, 3. Continuously changed until n-1. The bottom line will be 2, 3, 4 until 1. The last term is 1 switched with n. Well, all the other elements remain unchanged. Only 1 is changed to n is changed to 1. To multiply 2 permutations together, we need to transform them into n order of permutation. Another term, n should be added to the first permutation. The middle elements of second permutation all will be remained unchanged. And this time, after performing multiplication between these 2 permutations, it will change from 1 to 2, 2 is changed to 3, continued with the same way down, and last, n-1 is changed to n is changed to 1. The permutation is actually from 1 changed until n. Therefore, we can see that through this kind of method, we can prove that any permutation can be written into the product of several swaps, which should be the starting point for this swap. It is not fixed. It can use different kinds of representation method. We can corresponding switch 1 to 2, 2 to 3, continuously change it until n, starting from 1, but we can also start from 2, written as 2 is changed to 3, 2 is changed with 4, until 2 is changed to n, 2 is changed to 1. Corresponding to what we have seen just now, for different starting points, its cycle can have different kind of representations. Then, are those representations have the same length? Actually, it is not a must. For example, we can see 1, 2, 3. It can be split into 1, 2 multiplied by 1, 3. Of course, we can also have a longer one. It is equal to 1, 2 multiplied by 3, 3. Then again multiplied by 1, 3, 3, 1. It means that actually it is corresponding to different kind of swap representation. Though they could be different, but they still have some common feature. For example, for any permutation, it needs to split into product of several swaps. Whether it has odd or even terms is confirmed. Why? We can completely think that the swap could be regarded as a certain type of subtraction. For example, if I wish to exchange 1 with k, L with k, then in turn, when we perform the swapping, we can assume that L minus k is exchanged with k minus L. And this time, for example, if I have designed a function, correspondingly, it took out L and k. Their corresponding functions has become several the product of the difference between xl and hk. Then we will realize if we change for once, what will happen towards the symbols of the functions. For this kind of swapping, if we want to have the same kind of effect, the parity of the unit number for this kind of swapping must be the same. Therefore, for this kind of swapping, each time need to change the function symbol, then to reach the same effect for this kind of swapping, its parity is unique. Then we will split all the permutation into two categories. One type is known as odd permutation. Another type is known as even permutation, which means there are some permutation which is a product of odd number of swaps. For example, like this one, it's corresponding to 1, 2, 5, 3, 7, 4, 6. How many swaps inside here? There is 3 swaps. Then it is an odd number of permutation. And how about this one? 1 is still 1, 2 is still 2. All the elements, all 5 elements will be exchanging within themselves. And this time there's no swapping. It is an even permutation. And the odd permutation and the even permutations are parallel to each other forever. It cannot equal to each other. And this time we will use this kind of thought to solve this problem, which is a 华容道 of numbers. We can see from this kind of grid, it is a 4 times 4 of grids. Inside we have placed a 0 until 15. Then through swapping, it can produce another result. For example, we can see that such a corresponding 0 until 15 kinds of arrangement through several swaps, we will generate a new image. Then we may ask a question. Since the swaps can generate new images, if I limit any change to be the swapping of 0 with other numbers next to 0, which is 0's neighbor, then we will ask, under these rules, is it possible to produce the right image? We can all think about it first. Let's analyze it. 2 images over left and right. First, we do not consider the constraint of this 0 exchanging with its neighbors. What kind of permutations would it be? We will realize its permutation can be written as several swaps. In total, there are 7 swaps. In order to transform from the left image to the right one, an odd permutation is needed. But if we looked back, corresponding to our requirements, if each time the swapping is 0 and its neighbor for the swapping, then what will happen? We will realize 0 actually its position does not contain any change. Then we can guess 0 is swapped with above neighbor. Then come back by pair swapping. Therefore, it is definitely going through uneven steps to be back to its original position. Because we will realize with the constraint that swaps should be within 0 and its neighboring position, these 2 images should be go through an even permutation. But towards the swapping of other elements, we know it is an odd permutation. Odd permutation is not possible to have the same effect of an even permutation. Therefore, if we limit any change to be 0 and its neighboring position, it is not possible to produce the right image from the left one. Since we know that all of the permutations can be categorized into odd permutations and even permutations, then we can take out all the even permutations. It has formed a subgroup of Sm. We name it as an alternating group. Normally, we use An to represent. Why is it a group? We can imagine that it still contains the characteristic of closure, because even permutations and even permutations multiplication may definitely still be an even permutation. Permutation multiplication by right has already satisfied associative law, while identity element consistently corresponding to all the situation of all fixed elements. Its permutation is 0 time. It is an even permutation. And what about its inverse element? Corresponding to I is changed to K, K is changed to I. Therefore, its inverse element is still always an even permutation. It has explained that corresponding to all even permutation will form such a set, may generate a new group. We use An to represent. But how many elements are there? And we know that all the Sn contains an An and corresponding to other odd permutations. An add up with Bn, which is the sum of odd permutations and even permutations. It should be equal to the n factorial. And we know an odd permutation, it is multiplied by an exchange if it will form an odd permutation. Therefore, corresponding to the number of odd permutation must be less than or equal to the number of even permutations. Well, at the same time, an even permutation multiplied by an exchange will again get an odd permutation. Therefore, we managed to prove that odd permutation and even permutation have a one-to-one relationship. Therefore, the number of elements in An is equal to the number of Pn in the alternating group. The number of elements should be the number of all the full arrangement divided by 2.